Hello everyone and welcome to the third lecture of week 2. In first two lecture of this week we learned about natural gas properties, and in this third lecture in the part of natural gas production we will try to understand how the rock properties can be estimated and how they are going to influence the production of natural gas. So, let us see what we gone through in the last two classes. Comprehensively it can be summarized that the natural gas which is being produced from the reservoir to surface, and there it is getting refined and further it is transported. The properties of natural gas need to be estimated because natural gas is compressible in nature. Its compressibility factor also changes with temperature and pressure. Thus, it is important to understand how these properties can be estimated at different temperature and pressure. Those will help us to design the equipment and facilities and the maximum utilization of the facilities to process and transport the natural gas. So, we had learned about several properties. In summary, it is gas specific gravity, pseudo-critical properties. Important one is viscosity. The viscosity of natural gas is very low compared to oil and water. It is in the magnitude of 0.01 to 0.04 centipoise. Density, compressibility factor and the properties, those relate the change in volume from under one condition to another condition, formation volume factor and expansion factor. And these are interrelated properties, like density need compressibility factor, and later on you will see the Reynolds number needs density viscosity. So, the reservoir fluid that is getting produced from the formation domain, that is porous in nature, several factors are responsible for the production of fluid. That is the number of flowing fluid in the reservoir. The fluid like gas, oil, water, are they present, what quantity they are present. So, in our case we are having the gas. When we deal about the natural gas alone, we assume like it is just 100% natural gas, 100% saturation of the natural gas, or the reservoir is saturated 100% with the gas only, that we assume. Otherwise, the number of flowing fluid affect the production. Types of fluid in the reservoir, what type, what is the nature of that fluid, it is compressible, incompressible, how the properties are getting changed, and the flow regime, that is transient condition or pseudo steady state condition, those are responsible to for the production. So, earlier time when the production is started, it is the production value is under transient time, and later on it is shift to pseudo steady state case. Reservoir geometry, like the flow is happening in an axial direction, in a radial direction, is spherical, semi-spherical. So, altogether it is not only the fluid properties, those are important, but understanding the reservoir formation, its behavior for the production of fluid is also important to be understood. And in that case we are going to learn some of the properties of reservoir, those are related to natural gas engineering. There could be several other terminology, other definitions and other aspects of the reservoir, those should be understood by the reservoir engineer. In particular, those are dealing with the oil reservoir or the condensate reservoir, but in our case, as I mentioned here, we are assuming it is compressible in nature. We are in the transient and pseudo steady state conditions when the natural gas is being produced and the flow is happening under the radial condition. You will see all these things in coming weeks when we are going to set up the mathematical expression for how the fluid is flowing from reservoir to wellbore. In this regard, let us see some of the parameters, those help us to understand how the properties of the natural gas are going to be changed with the conditions, as well as how to represent those changes in the mathematical expression to understand the gas production. So, the parameter that we are going to use is a real gas pseudo pressure, denoted as MP. It is widely used for mathematical modeling of IPR of gas well. That I said, the fluid flow, assuming it is happening in a radial direction from all the reservoir corner to wellbore. So, this is our wellbore and this is reservoir. from this reservoir the fluid is travelling because of the pressure gradient, and you see here the pressure is very high, reservoir pressure, as well as pressure is high here, but relatively reservoir pressure it is low value, and the difference could be 500 psi or could be 1000 psi or could be more also. So, when the fluid or the gas is flowing from high pressure to low pressure region, we had taken the example of radial flow. The gas is going through several domains, several zones where the pressure and temperature conditions are different. So, the reservoir pressure changes from PE to PWF, that is responsible for the gas flow. We can assume the reservoir is isothermal with respect to temperature, that changes in the temperature is not that much, that could be assumed, but the pressure cannot be assumed like this, because the flow is happening because of the pressure gradient only. And when fluid is flowing from reservoir to wellbore, it is going through several pressure zones, and at each point when the fluid is having the experience of different conditions, the properties of fluid will change, especially the viscosity and compressibility factor. So, there is one parameter pseudo pressure that says when the fluid is having different conditions to pass through from one point to the other point, you can club them, you can lump them in the form of 2p by mu z, where the effect of viscosity and compressibility can be combined and integrated from Pb to P to represent all the changes are happening. And that gives us like a flexibility or a very approximation tool that says any changes are happening could be represented in this form. One of the simplest way could be, we can just say the average pressure could be used to evaluate the viscosity and compressibility factor. So, for example, the pressure is PWF here and P here, we can take the average of this, and after taking the average of these, we can evaluate the compressibility and viscosity at that pressure, but that is not going to represent the changes the gas is facing throughout this production process. So, the pseudo real pressure, that has got lot of acknowledgement in developing the inflow performance relationship, where the lumping these mu and z can allow us to account the changes happening in this lumped parameter because of the pressure. It is a pseudo property of the gas because it depends on gas viscosity and compressibility factor, while compressibility and viscosity both are the function of pressure and temperature. Thus, this property is called the pseudo pressure property. How to calculate that? So, if we see, we can prepare a table, or the procedure can be explained like this. When we are having a pressure, if you see here, the lower limit of this integral sign is Pb, that is any base pressure. We can take atmospheric pressure as a base pressure, that is 14.7 psia. We can integrate this to the pressure of interest. So, for example, I want to know the MP value here at the wellbore condition, that will be MPWF. If I want to know at the reservoir condition PE, here I want to know, it will be MPE. So, to know the value of this pseudo pressure MP at a particular pressure, what we can do? We can divide the pressure range from base pressure to the pressure of interest in a small segment. As a small segment, we are having the integration by the trapezoidal rule will be more accurate. And at each pressure, we can calculate the viscosity, compressibility factor, and this parameter, lumped parameter 2p by mu z, and then by doing the trapezoidal rule, we can calculate MP. Knowing this, we can also plot how the MP is changing with respect to pressure. So, at a particular point, when we are having a different pressure, we can represent the changes of pressure for viscosity and compressibility in this MP form. Another parameter similar to MP is NP, that is called the gas normalized pressure. This is with respect to reduced pressure, and only the compressibility factor is accounted for the change. It is assumed the viscosity, it will be dealt separately, but how the changes are happening in compressibility for the pressure range from 0 to reduced pressure or the pressure of the interest can be accounted with the help of this expression NP. But this is not used widely in the gas industry. The more important is MP, and you will see when we will be developing the relationship for IPR curve, you will see how MP makes the job easy However, it needs the computational technique, any Excel program or MATLAB program or any mathematical program that can integrate this function 2 Py mu z from Pv to pressure of interest. Another parameter that we will have frequently when we are transporting the natural gas through the pipeline, not only during the transportation, while in production also, when the fluid reached wellbore bottom part, it travels from wellbore bottom to wellhead, and the long distance is travelled. The parameter that comes into picture is Reynolds number. The Reynolds number is the ratio of inertial force to viscous forces, but in mathematical sense it is written as rho V d by mu. Rho is the viscosity of the fluid which is being flowed, V is a velocity, it is actually the apparent velocity that can be written as flow rate per unit area, volumetric flow rate per unit area, d is the diameter of the pipe and mu is the viscosity of the fluid. So, in case of natural gas production, when we are having natural gas is being produced from this wellbore or being transported through the pipeline, we know the diameter of the pipe. The viscosity term that we know, it depends on the pressure. So, the viscosity can be evaluated at average conditions. So, we can write this mu 1, that means we can evaluate viscosity at average temperature and average pressure condition using the correlation given or discussed in the last lecture. This rho, the density of the gas, we know density is m by v. The m is mass of the gas, that can be written in the form of number of moles of that gas, molecular weight, or that is again the apparent molecular weight, because natural gas is a mixture, and this apparent molecular weight can be converted into specific gravity multiplied by the molecular weight of the air, that is 28.97. So, we can convert this. If we write this here, what we are going to get here, rho, that is replaced by n gamma z 28.97. We can replace this V by Q divided by A. A is the area of the pipe or cross sectional area of the pipe, that we can say pi d square by 4, then d is here and divided by viscosity, that said it is evaluated at under the average condition. Now, what we can do, this volume will also be here, this is V. So, by the real gas law, we know P v is equal to N Z R T. So, we can write N by V is equal to P by Z R T. We know the R is a gas constant, the value is known to us, 10.73 in the US field unit system or 8.314 in a SI unit system. So, depend the unit system has been chosen. If we represent all of those, we are going to get this expression. Here one more analysis, one more correlation, that says P1, Q1, Z1, T1 at one condition. So, PQ, ZT at condition 1 is equal to PQ, ZT at condition 2. We can use the standard condition, pressure and temperature in this expression. If we write here, we are going to get the Reynolds number in this form. And you see Reynolds number in this form is a function of gamma g. So, we need to know the composition of the gases, the Q production rate under standard condition, standard pressure, standard temperature, diameter of the tube and viscosity. So, the Reynolds number when the fluid is being flowed, that is also going to change with the temperature and pressure the gas is going to experience. And the Reynolds number is very important when we are flowing through the pipeline. We understand the flow is under turbulent condition or under the laminar condition. It determines the friction factor, the roughness of the pipe is used with the help of Reynolds number to determine the friction factor value. So, Reynolds number itself is a function of temperature and pressure. If we put the standard condition of temperature and pressure, we are going to get this expression here. It is very important, again the coefficient, numerical coefficient appearing in Reynolds number or any other term depend on the unit system has been chosen. So, here P is shown in the PSI, Q is in MSCF per day, D is in inches, that should be remembered, it is not in feet, but it is in inches, mu is in centipoise, and temperature it is in the absolute unit system degree ranking. So, knowing as much as accurately the fluid properties will allow us to calculate the accurate Reynolds number, and that accurately calculation of the Reynolds number will allow us to calculate the friction factor, and this is very important parameter that we will be using very frequently. Another things, knowing the properties of the gas, we can also estimate gas in place, as I already mentioned previously, like the PV ZT when R is constant, a gas constant that can be taken out. So, at a one particular temperature pressure condition or the volume condition, one set of the data can be transferred to another set of the data using the real gas law, and that is with respect to base. We can convert any data set to the base condition or to standard condition as we use during the calculation of Reynolds number. Similarly, we can also express the same thing with respect to the flux also, P1 Q1 Z1 T1 is equal to P2 Q2 by Z2 T2. Under the standard condition, we assume Z2 as a Z2 at standard condition is 1. So, we assume the natural gas under standard condition will behave as a ideal gas. So, initial gas in place can be calculated with the help of this expression Bg, the volume of the gas under standard condition to reservoir condition. So, if we know the Bg value, we can use this expression and can find out how much gas reserve is available in a particular reservoir domain, and here you see it will depend on A, this is area, reservoir area in the unit of acres, and the numerical coefficient that we are seeing here is 43560. This is a conversion of acre to feet square. So, if we convert this acre to feet square, we are going to get this 43560 numerical value for the multiplication part. H is the page on thickness or the net thickness through which the fluid is travelling from the reservoir to wellbore. Phi is the porosity and Sg is the gas saturation. So, here you will see when we are using the knowledge of the gas properties to estimate the gas reserve or the gas in place in the reservoir, we also need to understand several terms, those are related to reservoir. So, in the further slides, we are going to understand more about the reservoir and its properties, those are related to natural gas production. So, reservoir rock properties are very important because they provide us the information or the knowledge about the gas is or the fluid is available in the reservoir domain or not, how much is the how much volume of a particular phase is available, and they also allow us to design and implement the gas or fluid production scheme from the reservoir. So, the reservoir rock property study comes under the head of petrophysics that counts for the study of rock properties and rock interaction with fluid. So, within the reservoir we are having the rock and fluid. The rock could be of different types, depend on the formation is composed of. It could be just a loose sands or unconsolidated sand, or it could be very tightly packed sandstone, limestone kind of the reservoir, depends on the geological time scale. The other parameter, those we are not going to cover in this, we just going to understand the properties, those are related to natural gas production. So, the petrophysics include the study of rock properties and the interaction with the fluid. These physical properties of the petroleum reservoir can be estimated either theoretically or performing the laboratory experiment. The important properties can be counted as porosity, that is the void in the rock. So, the rock that appears like it has no porous or it has no place to be in the form of void, but yes, it is having significant voids, depends on the size of those voids. So, every rock is having the porosity that may vary from 2% to volume percent to 40%, 50%, like the unconsolidated sand is having very high porosity, while the tightly packed shell are having very low porosity. That porosity actually depends on several factors. So, here I have listed some of the properties, those are related to natural gas production like the porosity, permeability, fluid saturation, capillary characteristic, compressibility, net pay thickness, fluid rock interaction, reservoir heterogeneity, and all these properties in one way or other way are going to be included in the natural gas production study. Important properties are porosity and permeability. Porosity accounts for the voidage in the rock. Permeability, it is a ability to move from one pore to another pore. So, the permeability actually decide the fluid or the hydrocarbon or the gas available in the reservoir is recoverable or not. As it can be seen in this picture, the pores are there. So, these are the pores. Those pores may be connected or may not be connected. The gas may be stored here, but that may be recoverable or not recoverable, that is determined by the permeability of that rock. So, if it is permeable, then only it is recoverable. Other properties like fluid saturation, those are like which part of the rock is occupied by the gas and which part is occupied by the oil, and when both oil, gas as well as water, all phases are available in a pore domain in the reservoir at one place, how they are going to occupy the places in the pore region is determined by the fluid saturation. Every properties could be important, like net pay thickness, that means this is the thickness of the reservoir that contributes to fluid recovery. So, reservoir like it is a very big area where we are having a wellbore perforated, and in this reservoir, for example, this is the porous region where the fluid is accumulated. We want to produce that fluid. When we are injecting our wellbore, at the bottom of the wellbore we perforate, we create the holes in that wellbore bottom part, and the fluid travels. Assuming it is a radial flow. So, the radially fluid travels from all the direction towards the wellbore, and only a part of the wellbore that is actually allowing the fluid to travel is a net pay thickness. In fact, the fluid may be available in large area, in the large height, that can be accessed for the production, that is called the gross page on thickness, but the net page on thickness is the thickness through which the fluid is coming to wellbore. Fluid rock interaction like the bathyability, that is also affect. Reservoir heterogeneity, variation in reservoir properties. So, the reservoir properties like porosity, permeability, saturation, compressibility, page on thickness, all they vary from location to location, and the heterogeneity should be accounted when we are going to understand comprehensively how the reservoir properties and how the reservoir domain is going to contribute towards the recoverable hydrocarbon production. The rock property data are essential because they quantify and also calculate the distribution of the hydrocarbon in the rock. When these properties are combined with fluid properties, they control the flow of the existing phases within the reservoir. So, assuming reservoir is having oil, gas and water, how they are going to be produced determined by the rock properties as well as fluid properties, and the reservoir properties can be estimated either by the logs, performing the experiment in the laboratory using some established correlations, or some maps, those are available. It is very tedious job, it is very complicated job knowing the entire reservoir spectrum, how the porosity, permeability, fluid saturation are distributed. So, sometimes those are calculated either on average basis based on the experience, and some other parameter correlation are used to correct the properties. We are not going to detail of that, but one by one we will try to understand more detail about some of the important properties here. So, like the porosity measure of the storage capacity. So, a reservoir is having several voidages, that voidage could be in the range of just 2% or less than 2% to 40% or 60% of the total volume of the rock, but only the volume that can accommodate the fluid or the pore volume contributes toward the porosity. So, the porosity by mathematical definition, it is the pore volume divided by bulk volume. So, for example, we are having one core plug sample, and that is having certain height and certain diameter, we can calculate the bulk volume of that core, but this is not pore volume. Pore volume is something when we are using the pores of this core sample to store some fluid, or the fluid is stored in that core sample, that can be used to calculate the porosity of that core sample. So, the porosity is pore volume divided by bulk volume. Pore volume is also known as a void volume. So, the definition comes as void volume by bulk volume. Porosity further classified or defined in two other important set of terminology. Absolute porosity, that is represented by phi A, that is total pore volume divided by bulk volume, and the bulk volume minus grain volume is the total pore volume. So, this absolute porosity definition is similar to what is the general porosity definition, that simply says the total pore volume available within the domain of study divided by the bulk volume is absolute porosity, while effective porosity simply says the volume that is available, or the voids those are available in the bulk volume, is not going to contribute to the recovery of the hydrocarbon or production. It is only the interconnected pore volume. So, the pore volume those are interconnected can be used to calculate the effective porosity. So, the effective porosity by definition comes out as a ratio of interconnected pore volume to bulk volume. We will see with one of the example how this absolute porosity and effective porosity can be calculated. But in most of the engineering application or reservoir engineering application, this is the effective porosity that is used, because effective porosity is something that is actually account for the recoverable hydrocarbon. There might be plenty of hydrocarbons available in the reservoir domain, but only those are recoverable, those are found in the connecting pores are recoverable. The effective porosity, as it is shown in this picture again, these are the pores, and the pores which are connected will contribute for the production. So, let us take an example. We are having one sample, core sample, cylindrical core sample with certain diameter and certain height. H is the height. If this is a core with H is the height, and this is some area, cross sectional area is A. So, we know the dimension of our core, we can calculate the bulk volume. Now, this core is saturated with a fluid of non-property, non-density. What we can do? We are saturating this 100%. So, what we will come to know, the pores those are connected, the fluid or the fluid of non-density can travel only to those connected zones. So, we can calculate the weight increase of this core sample when it was 100% saturated with a fluid of non-properties. The increase in the weight is because of the effective porosity which is available in this core plug. So, we can calculate the effective porosities. Another definition, absolute porosity. So, assume like this core sample is crushed, and when we are crushing it, we just destroy the connected and non-connected terminology. We just simply said this is a sample. After crushing it, this is a sample which is having grain volume or the volume occupied by the rock only. We can calculate the actual volume of solid. So, once we crush it, mix it, we destroy the connecting and nodes also. So, we are going to get actual volume of the solid. Knowing the actual volume of the solid and the bulk volume that was already there before crushing it, we can calculate the absolute porosity of this, and that absolute porosity simply because the isolated pores are counted. So, the pores which were not accessible before are also counted in this, and that is the absolute porosity. Here an example is shown. So, for example, this is height and area of the reservoir is known. We can calculate the bulk volume. A and H is the area, H is the height, and this is the numerical coefficient because of converting acre into feet square. Pore volume is simply this area, this volume multiplied by the porosity. So, by knowing the porosity, we can always calculate the pore volume or the connecting pore volume. Here the pore, if this is effective porosity. The reservoir rock porosity varies in all the direction, vertical and horizontal. Vertically it varies more than the horizontal section. In fact, even in from location to location the value varies. The node those are connected just here may not be connected just next 1 inch or 1 feet away. So, in a large domain of like kilometers region, there are large variation in the porosity value with respect to location. That can be classified as a vertical porosity variation or the horizontal porosity variation. And this picture simply shows like how the porosity is distributed in some domain. For that, what can be done? We can calculate the average porosity of the interest domain or the reservoir of interest. That average can be calculated in several form. First, arithmetic average, we can classify that several zones either vertically, horizontally, small segment, and we can say the porosity of a different region, the number of samples we are having. We can just simply sum the porosity of different core samples divided by the number of core samples. Number of core sample means, for example, this is our reservoir domain in a 2D manner. We are collecting the sample from a different location, the core sample, estimating the porosity of each. We can just take the arithmetic average. Other way could be thickness, weighted average porosity. In that case, we know the porosity changes with sample to sample. We can just weigh it with the height. Similarly, we can weigh it with the area or by the volume. Volume is again AIHI. AIHI is the volume of core I, which is having area AI and the height HI. So, the variation can be accounted by using any one of the formula, and that represent the average value of the porosity. Another properties is saturation. So, the voids those are available or those are connecting voids in the reservoir are filled by fluid. Those fluid could be water, oil and gas. So, the saturation of oil, gas and water is just a fraction of pore volume occupied by a particular fluid. So, if it is occupied by a gas, the volume of gas divided by pore volume is the saturation of the gas. Similarly, can be explained for the oil SO, that is volume of the pore occupied by oil divided by the pore volume. Similar for the water, the volume of the pore or the voids occupied by the water divided by the pore volume is the saturation of the water. So, the saturation can range from 0 to 100%. So, for example, in a reservoir domain there is no gas available, only the oil and water, then the gas saturation is 0. When the area is just having single phase, that is gas phase, the gas saturation is 100%. So, the saturation can range from 0 to 100%. The saturation of each phase that is available, gas, oil, water, the summation should be equal to 1. Critical gas saturation, another important parameter that determines like the condition above which gas begins to move or any fluid begins to move. When the fluid reach its critical saturation, then only it is start to move. Gas saturation increases as the reservoir pressure decline. So, what exactly the definition of the critical gas saturation is? When we are having the two phase gas and liquid, because of the pressure declination is happening in the reservoir, gas comes out of the oil phase and the gas saturation increases, and when this gas saturation reaches critical condition, just gas start to move. The average value of the gas saturation can be calculated in the weighted form, like it is weighted with the porosity as well as page on thickness Phi and Hi. Similarly, it can be estimated for the oil and water. Permeability, it is a property of the porous media that measure the capacity and ability of the formation to transmit the fluid. So, it is kind of the property of the rock that says the fluid can be passed, can be travel from one location to other location or not. It controls the direction movement of the flows. If the permeability is in x direction only, fluid will travel only in x direction, not in y and z direction, or any particular direction where the permeability is there, the fluid will travel, otherwise not. So, it controls the directional movement and the flow rate of the reservoir fluid in the formation. The permeability is defined by Henry Darcy in 1956 when he was performing the laboratory experiment under the laminar flow condition, when there was no reaction happening and only single phase was present. He had developed a correlation that says the apparent velocity is proportional to the pressure gradient and inversely proportional to viscosity of the fluid, and the proportionality constant came out as K, and that K is permeability of the, or means the ability of the rock that says the fluid can travel with that particular velocity, that can be converted, this apparent velocity can be converted into flow rate. So, velocity is called to QYA. So, area we got on the right hand side. The minus sign simply says length decreases when pressure increases, or other way, when pressure decreases length increases. That is why we are having the negative terms here. Important is this expression is only under the condition of laminar flow, no fluid and rock interaction, and only single phase is present. And in our case, when we are having the natural gas flow in the reservoir in the radial direction, when there is no reaction is happening, only gas phase is being flowed under the laminar condition, we can perfectly use Henry Darcy law to account for that. Here the permeability that we get is the absolute permeability. We will understand other permeability later on. So, here the apparent fluid flow velocity is V, the unit is meter per second, or it could be any one unit system. Here I had mentioned in the CGS system. Proportionality constant of permeability in Darcy, mu is viscosity of the flowing fluid, this is K that I forget to mention. The pressure gradient per unit length, Q is flow rate in centimeter cube per second, A is cross sectional area across which flow occurs, and altogether we get, with the help of this expression, we can get the Darcy permeability, and then 1 Darcy is equal to 1000 millidarcy. So, this permeability can be measured by passing a fluid of non viscosity through a core plug of measured dimension. So, for example, we are having a core, we know the dimension, the cross sectional area, the length of that core here, and flowing because of the pressure gradient, P1 is higher than P2, fluid will flow in this direction, and when we are collecting the flux at the outlet, establishing the relationship of the Darcy law, the proportionality constant we are going to get is permeability, and that permeability is absolute permeability. So, the permeability can again be the absolute permeability when we consider only one phase or one single phase is present in the system, means the permeability at 100% saturation of that fluid. It is a property of the rock and is independent of the fluid used in the measurement. Under the 100% saturation, it just becomes the property of rock, means how interconnecting pores are available in the rock. This assumes that the fluid does not interact with the rock. So, all these are the conditions of Henry Darcy. Effective permeability, when the reservoir is having more than one fluid, there is a competition of which one will travel first, which will get the preference from the reservoir to flow from one point to another point, and that is where the effective permeability comes into picture, and says the permeability of a fluid A when other fluid B and C are present in the domain. It is a function of the fluid saturation and the wetting characteristic of the rock. So, which phase is more having the wettability and non-wettability towards the rock will affect the effective permeability. Relative permeability is another term that is oftenly used in the reservoir calculations, that is the ratio of effective permeability to absolute permeability. Permeability depends again on the pore geometry, what type of the pores are, they are connected, not connected. Wettability means the interaction between the fluid and rock, and the fluid distribution, like how many phases of the fluids are present and how they are distributed, gas is on the top or it is dissolved in the oil. and the saturation history. Similar to porosity, permeability distribution is also there, because the pores are maybe connected here and just next 1 feet or next distance they are not connected. So, the porosity, like porosity, permeability is also having the distribution across the all the direction x, y, z, and again like the porosity, average absolute permeability can be calculated mathematically averaging the permeability. So, for example, first one is like arithmetic average, we can also go with the harmonic average and geometric average. They are just a representation, like different form of mathematically form will be used to calculate the permeability. It is like we are having a reservoir, or let us say we are having some domain of 2D, let us say, and we are having different zone of different permeability. We can consider the flow is happening from bottom to top or top to bottom, and because of different permeability of each layer, fluid will travel differently. To know the effective, or sorry, to know the average absolute permeability, we can average out the permeability of each section, and that can be done to calculate the average absolute permeability. Another important properties is battability, that is mostly used in the production of oil, more important than the gases. The tendency of one fluid to spread on or adhere to a solid surface in the presence of other immiscible fluid. So, when two immiscible fluid are in the pores or are in the domain and in the contact of rock, which one is having more tendency to adhere or spread on the surface of the rock is measured by the battability. The battability of reservoir rock to the fluid, it shows the distribution of fluid in porous media. So, which is having more affinity towards the rock, it will go towards the rock, other will be on the other side, and it is measured in the form of contact angle, that characteristic of the liquid for the solid. If the contact angle is 0, it means complete battability, the oil, the fluid is having complete battability, is it adheres or it is stick to the surface of the rock. When the angle is 180 degree, means it is complete non-wetting situation. So, with the help of battability, we can understand which fluid is having the access to enter in the pore or coming out of the pore region, depend on the battability behavior of that fluid with respect to rock. Other definition is surface tension and interfacial tension, those often comes. The forces at the interface when two fluid or two immiscible fluid are in contact. This is measured in force per length. Surface tension is between the liquid and gas, while the interfacial tension when the two immiscible liquids are in the contact. These expression can be obtained just simply by equalizing the surface tension force at the interface by the gravity forces, and when we do that thing, we can get the expression for the surface tension and expression for the interfacial tension, and those depends on the density of the phases. Here in the surface tension case, we are having for the water, this is gas water system, where we assume the density of the gas is negligible. We are going to get this expression. When in the case of two liquid, when we are having oil and water, the density of both the phases are going to come into the mathematical expression to account for the forces those are acting at the interface. Rock compressibility, like the fluid compressibility, rock compressibility also becomes important when we talk about the pore volume available in the reservoir to be occupied by the fluid. As we know, we go down, the reservoir is subjected to an overburden pressure. So, it is assumed like when we are going down 1 psi per feet, the pressure should increase, but because of the pore volume is available, it is just 0.5 psi per feet depth, because the rock does not, the pores in the rock does not experience the overburden pressure completely. The difference between the overburden pressure and internal pore pressure is called effective overburden pressure. During pressure depletion process, when we start producing the fluid from the reservoir, the internal pore volume decreases. When the internal pore volume is decreasing, effective overburden pressure increases, and when this process happens, the bulk volume of reservoir rock is reduced, and sand grain within the pore space, they start expanding, and because of these two things, the pore volume available for the bulk volume available in the reservoir as well as the pore volume both gets changed, and the properties those are responsible, those are depend on the bulk volume of the reservoir also get influenced. Mathematically, the core rock compressibility is defined as change in volume with respect to pressure at isothermal condition divided by the initial volume. So, any change in volume with respect to pressure divided by the initial volume is the rock compressibility. Because of the overburden, when we are going to a different depth, the overburden pressure will be different. When we are producing, the pressure, internal pore volume pressure will also be different with the time, and thus the rock compressibility will also be different. Another application of Darcy law that we will be using when the flow is happening from reservoir domain to wellbore, that can happen under the linear condition or in a radial condition. Radial condition, when we are having reservoir to wellbore flow is happening from all the direction radially. Linear flow, when we are having some experimental setup or the reservoir domain in such a way when the flow is happening only in one direction linearly. So, here we are having fluid and this is just traveling towards one direction where the production well is. We can use the understanding of the Darcy law to establish the relationship how the flow will happen because of the pressure gradient, and both the cases under the linear flow or the radial flow we are having Q as a function of other pressure drawdown P1 minus P2 in the linear and reservoir minus wellbore pressure here with other properties like here. Several assumption has been made here, like the viscosity is not changing, the Q is also constant, reservoir is homogeneous, most of the properties like the permeability is not changing with respect to direction in the reservoir. We will see the application of Darcy law when we will be developing the relationship for the IPR. We will get almost this kind of the expression that says how the Q flux is related to the pressure drawdown, the radius of the wellbore and the reservoir, viscosity of the gas which is being produced, K is permeability and H is the Pajon thickness. So, using the Darcy law, again we have to emphasize Darcy law is applicable only for the laminar flow condition when there is no interaction between the fluid and rock is happening and only one phase is present, either gas or oil or water. In our case, we are going to use the gas flow is happening radial direction from reservoir to wellbore. In summary, the fluid properties, there are several fluid properties those influence the performance of any particular process or particular equipment. Thus, to understand the performance or designing of the equipment or understanding the production system, we need to measure the properties of natural gas, and those properties changes with the conditions like temperature and pressure and composition. Similarly, understanding of the reservoir rock is also important, especially when we are having the objective of knowing the gas in place and what maximum rate gas can be produced from the reservoir. And on all these calculation, if we see, we are having several parameters those are appearing like the Reynolds number. The value of numerical coefficient on Reynolds number depends on the unit system chosen for each parameter involved in the calculation of Reynolds number. Similarly, when we are having the expression for gas in place, we are having the area, Pajon thickness, porosity. When we are having the Darcy law, we are having the permeability there, Pajon thickness there, pressure there, viscosity there. It becomes very important to understand how to convert from one unit system to other unit system. The dealing with the reservoir calculation done in US field unit system. Here I have summarized a small table that is taken from one of the reference that says from US field unit system how to convert into SI system or the reverse. So, for example, the area in US field unit system it is given in acre, while in the SI unit system it is meter square. So, the conversion should be applied. Similarly, for the other, especially for this gas production system where it is in US field unit system it is MSCF per day, while in SI unit it is meter cube per second, and permeability in US field unit system it is milli-Darcy, while in SI unit system it is meter square. You can prepare your own comprehensive list for all the calculation or for all the conversion, those will be appearing in several calculations. With this, I think we are ready to understand natural gas production, where we are having the identified well location, the reservoir location where the gas well can be drilled and the production can be started. So, in the next week we are going to establish the relationship for this segment IPR, inflow performance relationship, where the fluid will be travelling from all the direction radially towards this bellbore. The pressure PWF is lesser than the reservoir pressure, that is the driving force for the fluid to travel. And in our case of the natural gas production system, we are going to assume only single phase is present. Some amount of the water, some amount of the oil, some amount of the sand particle may be present, but we will treat them as negligible. We are going to assume our gas is compressible in the nature and establish the relationship for the pseudo steady state condition and transient conditions. I already mentioned the flow we will consider under the radial condition. So, with this understanding, we will go to establish the IPR relation in next week. Thank you very much for listening the video.